This video is about a basis for a vector space. We've got four objectives. First, we're going to define what a basis is. Then, given a set of vectors, we're going to show whether that set is a basis or not. Then we're going to look at some bases for common vector spaces. And then finally, we're going to look at orthonormal bases and see why those are useful. As we often do, we will start with some definitions. First, we define a relation of linear dependence. This is very similar to the definition that we saw before, but now it's defined for an arbitrary vector space V. So we saw this definition for Cn earlier. In this video, we're going to define it on an arbitrary vector space V, and the same with the other definitions that will follow. So given a vector space V, an arbitrary vector space V, and this subset S of vectors u1 up to up, and a set of scalars, alpha 1 up to alpha p, this equation is a relation of linear dependence. So on the left-hand side, we've got a linear combination of the vectors with the alphas as the coefficients, and on the right-hand side, we have 0. The trivial relation of linear dependence is this one, where all the alphas are 0. Then we define a set to be linearly dependent if we've got a vector space V and a subset S. That set is linearly dependent if there is a non-trivial relation of linear dependence. So here's the trivial one, where all the alphas are 0. And so if I've got a relation of dependence down here, where at least one of these alphas is not 0, some of them might be, but as long as they're not all 0, that's a non-trivial relation of linear dependence. And if one exists, even just a single one, then we say that set is linearly dependent. And then finally, we define linearly independent simply by saying that a set that is not linearly dependent is linearly independent. We will say that a spanning set of a vector space is a set that satisfies this equation. So S is a spanning set of V if the span of S is equal to V. And then we also say that S spans V. Now we come to one of the important theorems in this section and really in the course, the unique representation theorem. It's VRRB in the book. If B is a set of vectors, B1, B2 up to Bn, and it's linearly independent, a linearly independent set, and it's a spanning set. In other words, the span of this set B is equal to V, then any vector, say u, in the vector space V can be written uniquely as a linear combination of the vectors. So here is this vector u written as a linear combination of the vectors in the set, and this set of scalars, the alphas here, alpha 1, 2, 3 up to n, is unique. And really the only thing that this theorem claims that's not just part of the definition of a spanning set is that this set of scalars is unique. For the sake of time, I won't go through the entire proof here. Make sure you read through that in the lecture notes. I'll just point out that it uses the standard approach for proving that something is unique. If we want to prove that this set of scalars is unique, we assume there's another set that satisfies the property that these scalars satisfy, namely that they are the coefficients of the basis vectors whose linear combination is equal to u. And so u is equal to the alphas times the b, u is also equal to the gammas times the b, and then you eventually show that all the alphas and the gammas are equal. So this set is really just the same set, and therefore the scalars are unique. Now we get to the main topic of this video. We say that a basis for a vector space V is a linearly independent spanning set of V. So we defined what linearly independent means, we defined what a spanning set is, and now we're saying that a set that is both linearly independent and spanning is a basis. And really, basis is just a nice short name for linearly independent spanning set. Then we say that a vector space V is finite dimensional if some finite set of vectors in V spans V. In other words, if V has a spanning set with a finite number of vectors in it, then it's finite dimensional. In this class, we only study finite dimensional vector spaces, but it's important to know that there are other kinds, and in particular, infinite dimensional vector spaces. Those are used in some science and engineering fields. Hilbert space is one that you may run into later. Next, we have a couple of theorems that we saw in the column vectors chapter, and they're essentially just copied and pasted here. The only change is instead of Cn, I say vector space V here. But other than that, these are just the same theorems and proofs from the vectors chapter about column vectors. So I won't go through these again. I'll just read through them quickly so we can keep in mind what they say. If we have an indexed set of vectors here, If there are two or more of them, it's linearly dependent if and only if at least one of the vectors in the set is a linear combination of the others. This is a handy theorem to use when we want to decide if a set is linearly dependent or linearly independent. If we can show that one of the vectors is a linear combination of the others, well, then that means it's linearly dependent. The corollary of that theorem is a little bit stronger statement. It says that if we have this set of two or more vectors and it's linearly dependent, then one of the vectors is a linear combination of the preceding vectors, not just the other vectors in the set, but the ones that come before it. Okay, here's a new theorem that we haven't seen yet. This is called the spanning set theorem. If we have a set S of vectors v1 up to vp in a vector space V, and we call the span of S H, then we can say these two things. If one of the vectors in S is a linear combination of the other vectors in S, so say v2 is a linear combination of the other vectors in the set, then we can remove it from S, and S will still span H, meaning H is still equal to the span of S. So if v2 were a linear combination of the other vectors, we just take it out, and we don't change the span of S. It's still equal to this same set it used to be. The second thing we can say is if H is not equal to the set that contains a zero vector, then some subset of S will be a basis for H. So really, we can think of the spanning set theorem as the how to find a basis theorem. So if we're given a set of vectors, we can check to see if it's a basis, and if it's not, we can turn it into a basis. So if we're given a set, and we'll do an example of this soon, and asked, is this set a basis? Well, we check to see, is it linearly independent? Is it a spanning set? If it is both of those, then it's already a basis. But if it's not a basis, we could turn it into a basis by finding the vectors here in statement 1 that are linear combinations of the others and take them out until none of the vectors in the set are linear combinations of any of the others. And then we check to see if it's linearly independent. If it is, and it's a spanning set by this first part here, then it's a basis. If it's not linearly independent, well, it's a spanning set by part 1, and then by part 2, we can find a subset that is a basis. In other words, we keep removing vectors until there are none that are linear combinations of the others. And by the previous theorems, that tells us that the set is linearly independent. The last theorem for now says that every non-zero finite-dimensional vector space has a basis. This may seem like not a very significant theorem, but it's actually quite important because if we're asked to find a basis for a vector space, it's important to know that one exists. That would be kind of a tricky question if we were told, here's a vector space, find a basis for it, and it turned out that there wasn't one. So this theorem guarantees that there will be a basis for every non-zero finite-dimensional vector space. Later we will take these restrictions off and show that actually the zero vector space does have a basis, and infinite-dimensional vector spaces also have a basis, but as I said, those vector spaces, those infinite-dimensional ones, are beyond the scope of the course. The proof of this theorem is short enough we can go through it here. If V is a non-zero finite-dimensional vector space, by definition, V has a spanning set. In other words, by the definition of finite dimensional, remember a vector space is finite dimensional if it has a spanning set. So it's got a spanning set. Call this set B. If B is linearly independent, it's a basis. If it's linearly dependent, then by the spanning set theorem or the how to find a basis theorem, where H is equal to V, some subset of B is a basis for V. So we know that the basis exists. Okay, so let's do an example. Let's say we're given this set S. We've got 4 column vectors in C3 here, and we want to find a basis for the span of S. Okay, well, probably the easiest way to do this is to use the theorem from the previous chapters about how to find a basis for the column space. In fact, in the book, there's a theorem called something like basis for the column space. So in the book, they use the term basis before we really know what that word means. But remember, that's just a linearly independent spanning set. And what we do is we take these vectors and construct a matrix using those vectors as the columns, and then we row reduce that matrix. Okay, so by construction, the column space of this matrix A is equal to the span of the set S. So remember what this means. The C with A in parentheses, this is the column space of A, and the column space of A is the span of the set of column vectors of A. Well, S is the set of column vectors of A by construction. In other words, we constructed A to be that way so that the span of S is equal to the column space of A. So this question is asking us to find a basis for the span of S. which really means find a basis for the column space of A, and we know how to do that from the previous chapters. So what we do is row reduce A, and then we find our pivots here. So we can see that the first three columns of the row reduced form of the matrix are the pivot columns. That means the first three columns of the original matrix are the pivot columns, and the corresponding vectors form a basis for the column space of A, and therefore for the span of S. All right, now we're going to look at some bases for common vector spaces, so common bases for common vector spaces. We'll start with probably the most common basis for the most common vector space, which is Cn, and the standard basis vectors are a basis for Cn. So before we just called these things the standard basis vectors. This was just a name before, but now we can see that this actually is a basis for Cn, and we can use the theorem that we just used. We can construct a matrix using these vectors as the columns. We can see that it's already in row-reduced echelon form, and here's my pivots. There's a pivot in every column, so the set containing all three vectors is a linearly independent spanning set from that theorem. In other words, it's a basis. This next one isn't quite so easy. We don't have a theorem to tell us how to find a basis for this vector space, so we'll go through this one a little bit more carefully. It's also not as common of a vector space, so we're working in the vector space capital M with a subscript mn. So remember, this is the vector space of m by n matrices, and this set is a basis for this vector space. Well, what does this say? So this is the set B, and then inside here, this B is a matrix, and the subscript KL here tells us which matrix we're looking at. So K goes from 1 to M, and L goes from 1 to N. So we're going to have two subscripts on our matrices. And the entries in those matrices are given by this little formula here. So the ij entry, so row I, column j, of matrix KL is a 1 if K is equal to I and L is equal to J, and it's a 0 otherwise. This is really a nice, short, succinct way to describe this set, but it's not at all obvious what the heck does that mean. So let's look at a specific case, in this case M23, and see what would this set be if I follow this algorithm for constructing this set. What would the set B look like? Well, here it is. So this is B11, B12, B13, etc. And we can see how that works up here. Basically what this says is you label the matrices with two subscripts according to the size of the vector space. So M is 2, N is 3. So the first subscript is going to go from 1 to 2. So I'm going to have some B1s and some B2s. So I got 3 B2s here and 3 B1s. Then the second subscript is going to go from 1 to 3. So I'm going to have a B11, B12, B13. So the second subscript goes from 1 to 3. And same thing here. On the 2s, so this is B21, 22, 23. And what this says is you take matrix B11, and in this position, row 1, column 1, you put a 1. Zeros everywhere else. That's what this says. For this one, we want a 1 in row 1, column 2 here, and zeros everywhere else. I want a 1 in row 1, column 3, and zeros. A 1 in row 2, column 1, zeros everywhere else, a 1 in row 2, column 2, and in row 2, column 3. So when you see it like this, hopefully it's a little bit easier to understand what this means. And really, when I do problems like this, I just kind of remember how this works. So when I wrote these out, I'm just thinking to myself, well, these basis vectors, so they're a matrix, a 2 by 3 matrix is a vector in this vector space M23. These basis vectors are going to be all zeros everywhere, except they're each going to have a 1 in one of the positions, and they each get a 1 in a different position. So I just go across the rows, and I have zeros everywhere, except I'll have a 1 here on this one, and then a 1 here on this one, and then a 1 here. So I'm just moving across each position in each matrix and putting a 1 in each corresponding place, so that every matrix has a 1 in one position and a 0 everywhere else, and they all have a 1 in a different position. And that's the key to how this works, as we'll see. Before we continue with this specific example, let's talk about how we can show that a given set is a basis in general, because we're going to use this technique for all of these problems. Every example where or every problem where we're given a set and we're asked to decide, is this a basis, or show that it is a basis. There's two steps. We want to show that it's a linearly independent set and also that it's a spanning set. And you could do these in either order. I just put them in this order. They're separate steps though. So to show that it's a linearly independent set, you do two things. First, you form a relation of linear dependence on the set, and then you show that the only solution is the trivial one. In other words, that the only relation of linear dependence is the trivial one, and that means that the set is linearly independent. Then to show that it's a spanning set, there's only one thing you need to do. You show that an arbitrary vector in the vector space, not in the set, but in the vector space, can be written as a linear combination of the vectors in the set. And if it can, that means that the set spans the entire space, since this is an arbitrary vector. And that's important. You can't pick a specific vector in the vector space. You have to use an arbitrary vector, and I'll talk about what that means as we continue the example. Okay, so let's let A through F, A, B, C, D, E, F, be some complex numbers, scalars, and then what we're going to do is form a relation of linear dependence. So we're doing step one, form a relation of linear dependence. So I've got, here's my linear combination, here's my basis vectors, right, b11, b12, etc., and then set equal to the 0 vector. Well, remember, we're in the vector space of 2 by 3 matrices, so the 0 vector is the matrix that's full of zeros, okay? This matrix satisfies the 0 axiom for vector spaces. That's how we know it's the 0 vector. So if we simplify the left side, multiply all these coefficients inside here, we'll get an A in zeros and a B in zeros, etc., and add them all up. We get this matrix, which is equal to the 0 matrix, or the 0 vector. And using the definition of matrix inequality, if these matrices are equal, that means every entry in each matrix is equal. So A is equal to this, B is equal to this, C is equal to this. So they're all equal to 0. All these are equal to 0. So we just formed a relation of linear dependence and showed that the only one that exists is the trivial one. Remember, where all of the coefficients are equal to 0. So these all have to be zeros here. And so that means that the set is linearly independent. Now we show that it's a spanning set. We do the second step. We write down an arbitrary vector in the vector space. Well, a vector in this vector space M23 is a 2 by 3 matrix. And this is an arbitrary vector in that vector space. And what I mean by arbitrary is it's not a specific matrix with specific numbers here. I've used letters or variables instead of numbers. So A can be any complex number. B can be any other complex number. So I use a different letter here. C can be yet another complex number, etc., etc. So any vector in the vector space M23 can be written in this form. And then what I've done is I've written it as a linear combination of the basis vectors. Here's my basis vectors again. And I intentionally chose the same letters here so we could see how similar this looks to the relation of linear dependence that we just looked at. So if we go back up, here's my relation of linear dependence. Was the left-hand side of my relation of linear dependence is now the right-hand side of my linear combination. And it's the same linear combination here as up here. Up here, this is a relation of linear dependence because it's set equal to 0. Down here, this is a way to write an arbitrary matrix in the vector space. So we use this to get down to here to show that it's a linearly independent set. And then we use this to show that this is a spanning set, that the set containing these basis vectors is a spanning set. So the span of B is equal to M23. That means it's a spanning set. Since it's also linearly independent, it's a basis for M23. The last example we'll look at is a basis for Pn. Remember, Pn is the vector space of polynomials of degree less than or equal to n. And the basis is here. That's the set of polynomials 1, x, x squared, x cubed, x to the fourth, up to x to the n. If we look at a specific case like P3, that basis would look like this. It would be 1x, x squared, up to x cubed. So if we want to show that this is a basis for P3, we do the same thing that we did in the previous example. It's going to look a little different, but the steps will be the same. Just to review really quick, this is what we're going to do. We're going to show that it's a linearly independent set by forming a relation of linear dependence and showing that the only one that exists is the trivial one. In other words, all of those coefficients have to be 0. And then we'll show that an arbitrary vector in P3 can be written as a linear combination of the vectors in that basis. Okay, so here's my relation of linear dependence. So I form a linear combination of the vectors in the set, and I've used a, b, c, d as my scalars here. So a times 1, b times x, etc. Set it equal to 0. And now I solve for a, b, c, and d and show, my goal is to show that they all have to be equal to 0. Well, I'm going to do a little rewriting of this equation. So I'm going to take the parentheses off here. I'm just going to write a times 1 is just a. Okay, so I got my polynomial on the left side. Then I'm going to write 0 like this, 0 plus 0x plus 0x squared plus 0x cubed. And then we're going to set like terms on the right and left sides of the equation equal. When we do that, we can see the like terms set equal here. It's really easy to see then that all of these coefficients, a, b, c, d, all have to be equal to 0. And so we've shown that the only relation of linear dependence is the trivial one. So that means our set is linearly independent. Then we're going to show that an arbitrary polynomial in P3 can be written as a linear combination of the basis vectors. Why is this an arbitrary polynomial? Well, it's a third degree polynomial. It's got a constant term, an x term, an x squared term, an x cubed term, and it's got some arbitrary number, some unknown number for the constant term. Could be 0, could be a billion, could be minus pi, whatever. Some other coefficient on the x term, a different number on the x squared, a different number on the x cubed term. And we can use sort of the same trick we used in the previous example by writing this now, which is an arbitrary vector, as the same linear combination that we saw before. So I just chose the same letters as the coefficients for my polynomial, and so it looks very much the same on the right side as it did when I was showing that the set is linearly independent. So because this arbitrary polynomial can be written as a linear combination of the vectors in the set, that means that the set spans P3, because this could be any polynomial, any third degree polynomial can be written as a linear combination of the basis vectors. Therefore, the span of the set is P3, and since it's a linearly independent spanning set, it's a basis. Okay, the last objective we have here is to look at some theorems, and in particular theorems about orthonormal bases. The first theorem is an addition to the invertible matrix theorem. So remember, the invertible matrix theorem is a theorem about invertible matrices, and it's a logical equivalence theorem. So it's got a lot of statements that are all true together or all false together. They're logically equivalent. So we say that an n by n matrix A is invertible if and only if the set containing the columns of A is a basis for Cn. The invertible matrix theorem already tells us that a matrix is invertible if and only if the set containing its columns is linearly independent. Also, it's invertible if and only if the set containing its columns spans Cn. In other words, it's a spanning set. Well, a linearly independent spanning set is a basis. So now that we have a name for that, we're essentially just applying the definition of a basis to say, okay, well, if we combine these two statements, we can say A is invertible if and only if the set containing the columns is a basis. An orthogonal basis is a basis that's also an orthogonal set. So remember, an orthogonal set of vectors means that every vector in the set is orthogonal to every other vector in the set, and orthogonal means the inner product of those two vectors is 0. We say that a vector space that has an inner product defined on it is an inner product space, and it turns out that inner product spaces are really useful, as we can see here. So let's say I've got a vector y in an inner product space V. So some inner product is defined on that vector space V. So remember, we studied inner products in the column vectors chapter, and we saw the inner product that was defined on column vectors. Well, you can define inner products on lots of different vector spaces. So we may see some of those later in the course. So let's say that y is a vector in an inner product space V, so there's some inner product defined on it, and we have an orthogonal basis for the vector space consisting of the vectors u1 up to up. Well, then we can write y as a linear combination of the basis vectors with these coefficients alpha, and then for reasons that are not obvious, I'm going to take the inner product of the first basis vector here, u1, with y, and we'll see what happens when we do that. So I'm just going to replace y here with this expression, which I put in down here. Okay, so inner product of u1 with y, well, that's the inner product of u1 with this expression. And I use properties of inner products, and I skip several steps here. I can rewrite this side like this. I won't write out all those details. It would be a good exercise to see if you can connect from here to here using the properties of inner products. But once we get to this point, if we expand this sum, it looks like this, and we can see that this inner product is 0. This one's not 0. Remember, you can't have a 0 vector in a linearly independent set, so none of these vectors are 0. And if u1 is not 0, the inner product of u1 with itself has to be greater than 0. That was a theorem that we saw about inner products. But since this set is an orthogonal set, it's an orthogonal basis, that means u1 is orthogonal to u2. This inner product is 0, it's orthogonal to up, and all these ones in here are also 0. So these essentially all go to 0, and I'm just left with the inner product of u1 with y is equal to alpha times the inner product of u1 with itself. I can solve for alpha 1. I know that this is greater than 0, so I can divide both sides by this inner product. And I've got this little equation for alpha 1. That essentially proves this theorem. If I've got this orthogonal basis for an inner product space, any vector y in the vector space can be written as a linear combination of the basis vectors. And here's that formula that we just derived for the coefficients here. This may not seem like a big deal to be able to have a formula for these alphas, but if we think about how we would find these alphas, if we go back to this step here, if these inner products weren't all 0, if these zeros actually were non-zero numbers here, and if I was trying to solve for alpha 1 here, well, I'd have an equation with alpha 1, alpha 2, all the way to alpha p. I could get another equation with all those alphas if I did the inner product of u2 with y. And then I'd have a similar equation here, except that this would be u2 and u1, and then u2 and u2, and u2 and u3, and then u2 and up. And then I'd have alpha 1, alpha 2, and alpha p. So I could get a system of p equations in p variables, and I could solve that for the alphas. But I'd have to solve a whole system of equations for all the alphas all at once. With this equation and this formula for the alphas, I can solve for the alphas one at a time, and I don't have to solve for them all at once. So in applications, this is really, really nice. It really simplifies the computation of these alphas. And if that weren't enough, if we have an orthonormal basis, which remember is a basis that's an orthonormal set, and orthonormal means orthogonal and unit vectors. And a unit vector means that if I take the inner product of any vector with itself, like ui with ui here, it's equal to 1. Well, if this is equal to 1, this formula simplifies even more, which we can see down here in this theorem. If I have an orthonormal basis, then any vector y and v can be written just like this, and here's the alphas, but this goes away, it's just a 1, and so I can replace the alphas here with this inner product, which is what we've done here. So the proof essentially does what I just described. Okay, we're going to finish up with a couple of the theorems that I promised at the beginning. Every vector space has a basis, and as I mentioned, the proof is beyond the scope of the course. This implies beyond the finite dimensional vector spaces that we already saw a pretty simple theorem that said that every finite dimensional vector space has a basis. This adds to that theorem the zero vector space and infinite dimensional vector spaces. I do have a proof that the zero vector space has a basis. We'll see that in a minute. But the proof that infinite dimensional vector spaces have a basis is beyond the scope of the course. Here's the theorem, though, about the zero vector having a basis. So a basis for the zero vector space, remember, that's just the vector space that contains only the zero vector, over any field is the empty set, which is written like this. That may be very strange to think of the empty set as being a basis. It's a linearly independent spanning set. Well, it is. We have to do a little bit of leveling up our definition of span here. I just really included this for people who are curious. I'm not going to ask you about this. This isn't in the book, pretty sure, and it's not going to be on any quiz or exam. But just to be complete, for those who are curious, the zero vector space actually does have a basis. It's the empty set, and here's a proof. Okay, we made it. We defined a basis for a vector space. We saw how to decide whether a given set of vectors is a basis. We saw some common bases for common vector spaces, and finally, the usefulness of an orthonormal basis, in particular, how easy it is to calculate the coefficients of linear combinations of vectors when you got an orthonormal basis.